Okay, in this video, we will discuss the photochemical electrocyclic reaction. So in photochemical reaction, what we consider is the HOMO of the excited state electronic configuration. And if we look at the excited state HOMO, it is the opposite orientation of the outermost p orbitals compared to the HOMO of the ground state. So, photochemical electrocyclic reaction, the rotation fashion is opposite to the thermal condition. So, in this case, if you have an odd number of pi bond, the rotation is conrotatory. And if you have even number of pi bond, the rotation is disrotatory. Remember in the previous video, I've shown you that if it is thermal, it is odd, it is this rotatory. So if we have UV odd, it should be con-rotatory. It is because it is opposite to the thermal condition. Okay, so in this case, we can see that if it is this rotatory, you see the light phases are on the same side, but then the rotation, one will be counterclockwise, one will be clockwise. For conrotatory, the light phases is going to be opposite, and the rotation is both of the p orbital either will go clockwise or counterclockwise. Okay, let's take a look at the example here. We have 2E, 4Z, 6E, 246 octatriene. So this is UV, so it is UV, and we have odd number of pi bond, so it is conrotatory. So when it conrotatory, this both goes clockwise. So when this go clockwise, what happens is that this methyl group will go up, and then this methyl group will go down. So it will give you a trans product. Okay, let's take a look at hexadiene. Hexadiene has even number of pi bond, so it is U even, and it is disrotatory. So you notice that disrotatory, the light phases are on the same side. Okay, in this case, this methyl will go up, and then this methyl also will go up. So you end up having a methyl group at the same side, so it will give you a cis product. Okay, let's take a look at the example here. We need to identify compound A and compound B, and then label each process as conrotatory or disrotatory. Okay, for this question, it is a bit different because it involves ring opening. The previous example that we have shown is ring closing. But then, please take note that ring opening is opposite to the ring closing. So in this case, we want to open the ring of the cyclic alkene, and then to give a polyene. Okay, let's take a look at this reaction. Because it is a ring opening, so it is thermal, and then it is even, so it is disrotatory. Remember, when we have a ring closing, it is thermal, odd, and this. So because since it is opposite to the ring opening, okay, so ring opening we get when it is even number, we get this rotatory rotation. Okay, in this case, because it is this rotatory, one will go clockwise, one will go counterclockwise. So the CH3 will reside here, and another CH3 will go here. So we end up having this product. Okay, And then this product undergo photochemical reaction, and you know that uh, because this is ring closing, so it is U, and then it is odd, so it is conrotatory. So when it is conrotatory, the light faces are opposite, and then if you turn it around, so this CH3 will go here, and then this CH3 will also go down. So what you will get is a cis cyclohexene, cyclohexadiene. Okay, these are some of the example that we can work on. Okay, if we look at these all three questions, so this has been shown in the example of thermal electrocyclic reaction. But then, since we are using different condition, which is UV, it will give different types of compounds. Okay, for question number 1, um, this is UV. And so it is U. We have odd number of pi bond, and its rotation is conrotatory. So we draw the p orbital. You know, if it is conrotatory, it should be the same faces, the like faces should be opposite to each other, and it's going conrotatory. So what happens when it is going conrotatory? So this methyl group will go up, this methyl group will go, this will come here, and then will go up, and then this also will go up. So what do we get is a 6-membered ring, and then uh, the CH3 is at in front, and we will get a cis product. So this compound is opposite to the compound that we get in thermal condition. Now let's go for the second one, which is this is also UV, so it is even number, so it should be this rotatory. Then we draw the p orbital. You know, this rotatory, it should be at the same side, so clockwise, anti-clockwise. So what will happen is that this will go here. Okay, this CH3 will go down here, then this will go up. So we will end up cyclobutene with, okay, the CH3 up here, and then another CH3 is down. Or we can draw it properly. One is in front and one is at the back. So we get a trans product. And now the difference between question 2 and question 3 is the position of the methyl. So this is also this rotatory. So you will get this methyl group will go up, this methyl group also will go up. It will like this, both will go up, or we can draw it at the same side, or as long as it gives us a cis product. Okay, to summarize electrocyclic reaction. So electrocyclic reaction normally involve two types of mechanism. The first one is ring closure. The second one is ring opening. In ring closure, product normally has one more sigma bond and less one pi bond compared to the reactant. And in electrocyclic ring opening, product usually has one more pi bond compared to the reactant. And then this is a summary of reaction, number of pi bond, and the rotation. But this is for ring closing. You can construct a table on your own on ring opening. It's just that the ring opening is opposite to this ring closing. Thank you.